Good afternoon, this is Schweitzer. Let's walk through some content here on properties of ionic compounds. Now, ionic compounds, these are the main properties we will be looking at here. The properties that are the most important here as I grab my pencil. Really the bulk crystal is something that is probably the least actually tested question, but is the underlying concept for everything else. So not understanding or being able to recognize on the fly a bulk crystal and how it works is really what cascades to all the other questions as well. Alright, so let's just kind of walk through what we got here. Melting point, likely the most common characteristic that will actually be tested. What breaks when an ionic compound melts? Well, it takes a lot of energy, but you're actually breaking these bonds here. So it's really important to realize that an ionic bond is a bond that breaks when melted. We're actually going to start, as you heat this, you're adding increased kinetic, both translational and rotational motion, shaking them back and forth, spinning them, and eventually it shakes and breaks off. The whole thing just kind of earthquakes, starts fracturing things all along here and just plops down as liquid. You could also say that the ionic bond is really a form of Coulombic attraction. It's one of those things where on an AP test, would they mark that wrong for this? It'd be tough, but this is really more specific to the nature of the ionic compound. So what happens in a molecular substance when you warm up and break these things? I kind of described that already. Alright. 2 seconds here. Alright, so what controls the melting point of an ionic solid? Really important. So, charge times charge, right, distance squared. So, the first thing we look at here is the charges of these things. That's just generally the way we do this. So, the charge of the cation, charge of the anion. If the charges are the same, then we go to here, which we refer to as the internuclear distance. So in this case, we have, let's say, chemical A looks like this, chemical B looks like this. It'd be that distance from here to here. Okay. Notice how big the atom in number of energy levels ultimately separates them, making the attraction separates them, making the distance larger, therefore reducing the attraction. So larger distances cause lower attraction, lower melting points for ionic compounds. Higher charges on these things cause increased attraction as well. All right. So that is that one. Alright. So melting point methodology. Kind of alluded to this already. But first thing we do is let's consider the charges. So let's try this one once. ALS. It's aluminum sulfide. Has a larger or smaller melting point than NaCl. So students would at this point consider the charges. This is a plus 3 minus 2. This is a plus 1 minus 1. Okay. Therefore, we get plus 3 minus 2, and then we have a plus 1 minus 1. The size of the sign, positive or negative, really just means if it's attracting or repelling. So if it's negative, it means it's attracting. If it's positive, it means that it's repelling. But that's for us doesn't really mean much. But notice that obviously having a 3 and 2 here is going to be 6 times larger than the 1 and 1. Therefore, this guy here is going to be larger due to the sizes of charges as seen by Coulomb's law. The melting point of Al2S is likely to be close to 6 times larger than NaCl, assuming a similar radius. Alright. Alright, methodology. So 1, check. check the charge, but if the charges are identical, consider internuclear distance or radius. Larger radius equals less Coulomb attraction. So we're kind of showing a picture of this here. I started earlier. So really the attractive forces, let's flip this over to red. Okay, black is repulsive, attractive. Okay, so what are the things that are actually attracting here? Well, this electron is attracting to this nucleus. This electron would be attracting to this nucleus, attracting to this nucleus. This electron is attracting to this nucleus. This electron is attracting to this nucleus, just like this guy technically is attracted to its own as well. This nucleus doesn't really know that this electron is from its own atom and that this one is from a different atom. It just knows it's negative. And it attracts them either way. So, and again, we have this attraction here. Okay, now the longer the line I had to draw, the weaker the attraction. And of course, we also have some repulsive forces. Those are definitely going to be in play here. This is the reason why electrons don't crash into the nucleus. So we'll have some repulsive forces here, repulsive forces here, repulsive forces here, repulsive forces here, and you actually have repulsive forces here. Okay. So there's a balance between repulsive forces and attractive forces. But you should note here that this large distance here is really the problem as to why these two atoms would have a much larger attraction than these two atoms, or corresponding these two atoms. So larger distances equal lower attractions, and we call it internuclear distance. We know it's looking at the sizes of the atoms, but we want to talk about it in terms of internuclear distance so we can explain how it applies relative to Coulomb's law. Alright, so you'll see here on your particular page, these are missing, but you can fill yours in. So here we have a pretty good diagram that shows up quite often. It really is basing its whole thing on how the atom actually forms of attractive and repulsive forces. When you're really far away, whether it's ionic or covalent, there's minimal repulsion, but apparently a little bit more attraction than anything. But ultimately here they're saying there's nothing. Get them a little closer together, and the attractions that I pointed out earlier start to pick up, which is why it comes together. I mean, if it's going to repel from the beginning, then you're kind of a lost cause. It just goes the other way. But then eventually you get to the point right here where your attractive forces that are bringing the two together are really strong, but then your repulsive forces are equally as strong, and you are kind of in a teeter-totter point where you're balanced. Not a very balanced teeter-totter, but then if you were to squeeze them even really close together, then your repulsive forces start really picking up versus your attractive forces, and you're going to start moving away. So quite often, sometimes you'll see things online where this bond really looks more like a spring, where it's bouncing back and forth and vibrating, and that vibration actually can be picked up via infrared spectroscopy and different types of things. So either way, a couple things you might note is that this is my bond energy. So of course we know that triple bonds, for example, we would have a larger bond energy. So drawing this, a deeper one would be a triple, or a single might be a single. So we might look for something that would be around this depth for maybe a double, this depth for a single, respectively. And also we know from here is our internuclear distance representing. So we might expect for a triple bond to be more energy and shorter distance, whereas a single bond is going to have less energy but a larger distance between the two. So it might be, this would be shorter, but this would be longer. So maybe you have something like that for a single. And they'll see things comparing two atoms on here. Just still find ways to twist it and turn it. Okay. Alright, at this point, looking to order these things in terms of increasing or decreasing melting point. Go ahead, pause it, give it a try. Alright, so first thing I would do is kind of just jot out these ions. If you are still a little struggling with these ions, then let's keep that ion sheet close and keep working at it. it will eventually become part of your normal vernacular, and therefore minus 2. Alright, so highest melting point would be this guy here, ALO3, followed by, the next one would be, so that one's done, probably this guy right here, which has got the ALCL. It's 4 units, so ALCL3, that's next, and then we got this one, and okay, Na2O, and then the last two are where we're going to start comparing our second individual situation here, where it's going to be both +1 -1, and they'll always do it where the one atom is identical. That's how they're going to do it every time. So this chloride is really, in the fluoride, really what we're comparing ourselves to, and since this guy is farther down the periodic table, which of course we would never want to reference down the periodic table, you would really just want to say, okay, we got fluorine located right here, we got chlorine located here. All right, so why is it that the attraction it's going to be NaF goes first and then NaCl goes second? How would you reference this? You'd say, well, okay, chlorine, you would not say farther down the periodic table than making it larger. You'd say chlorine has more energy levels, making it larger, causing the internuclear distance to be greater. Therefore, reduced Coulombic attraction. That would be a perfect answer, reduced Coulombic attraction. That's how you want to step through that. Alright, moving along here. Okay, there's the answers for those. And then we got this guy. So this is a pretty common little question. You'll see these pop up occasionally. Take a look at it. And give us an answer here. There we go. There's the answer. Next one. Alright, another great question. Take a look at it. Again, you read the question and you got yourself, what does this question fall back on? Like, what content does it fall back on? Go back to your core ideas. What do you want to know? And there we go. Maximum charge, smallest radius, super common questions. Now they use a term here called lightest energy. You're like, I don't know what that means. That doesn't mean the problem's shot for you. It's just another term. You need to be able to work around some of these terms. Understand the core concepts haven't changed. Alright, why do things dissolve? Okay. First of all, anytime something dissolves, it's an attraction. Let's stop this video here just so it doesn't get too late, too long. We've covered our first property, which is that of melting points. And we'll pick up with dissolving next.